All right, so impact craters are grouped into two different types, simple and complex. Both impact crater types will experience the same process of vaporization, of melting, of ejection of material, of formation of the ejecta rims, and later they will experience the infilling that is. But how they differ is that simple craters are typically small, meaning a few kilometers in diameter, such as the Beringer crater that we looked at in the last slide, and complex impact craters may exhibit actually quite a different shape, also being bigger. So in a very small time period, maybe seconds to a few minutes, the size of complex impact craters can grow from tens of kilometers to more than 100 kilometers in diameter. Here, typically, the rim tends to collapse more quickly, and the center of the crater will actually tend to uplift following the impact. So on Earth, typically, any crater that is larger than 6 kilometers in diameter is a complex impact crater. And anything that is below that, so only a few kilometers in diameter, is a simple crater. Okay, but again, both of them will experience the same processes in terms of vaporization, melting of the rocks, nearby the ejection of some material up in the air. They will both form the ejecta blankets and the ejecta rims, and then both will experience the infilling inside of the crater by some sort of material, either that was ejected, or material from the body itself, or both, or later material even from the processes of weathering, erosion, deposition. So the geologically complex impact craters are tough to identify in truth, because they tend to be eroded away, or they tend to be infilled by sediment that is younger than the sediment that the impact caused to eject. So they can be eroded, much more like what is shown here, and they can also be infilled, or they can also be infilled, either way. So an example is an impact site in the Chesapeake Bay that I mentioned in the last slide. So here an asteroid or a comet, we're still a little bit unsure, that was 3 to 5 kilometers in diameter impacted the surface about 35.5 million years ago. This crater is now covered by what is a much younger sedimentary deposits. So as you're seeing here in the cross-section below, this used to be the crater, but everything now is covered by both much of the ejected material and then later on by much younger deposits on top of it. And you see that the layers here are about 1 kilometer in depth below the surface. So there's 1 kilometer of new material on top of what used to be the crater itself. So this crater is about 85 kilometers in diameter. At least that is what we understand from the remote sensing that we have done. Another good example of a complex crater is one that is especially highly eroded crater is the I don't even know how to say it, Manicouagan, I think so, crater in Quebec, Canada. So this is a 65 kilometer in diameter ring, as you're seeing right here, a ring. And it's a reservoir actually. So it's a reservoir shaped ring that is filled with glacially eroded material. So what used to be the crater is now infilled with glacially eroded material. That material is also what's surrounding it, but yet some of it remains relatively lower in elevation for the water to be infilling that ring-shaped area. So the reservoir outlines most of the crater, which was estimated to have been about 100 kilometers in size upon impact, but now it's a lot smaller, as you're seeing. However, they do believe that it's relatively centered. And this impact, they believe, happened about 215 million years ago, so much older than the one that happened in the Chesapeake Bay, which happened 35.5 million years ago. I also wanted to point out in the cross-section for the Chesapeake Bay that, as you're seeing, the metal part of the impact, the center of the impact, that area has been uplifted a little bit, which is one of the characteristics from complex impact craters, that the middle of the impact actually uplifts, and then the rest still stays a little bit lower. Table 14.2 in your book has a summary of notable impacts and airbursts of extraterrestrial objects. And in there it tells you the event or feature that, what it's named after, the location that it happened at, the age, so how long ago it occurred, and also the significance. So in some cases, it actually caused extinctions, or it caused major climate changes or things along those lines. So table 14.2 is really cool. I strongly recommend you look at it. If not now, maybe after the end of lecture, so you know what I'm going to be talking about throughout the quizzes and the lab and whatnot. So totally worth the read. Check it out. Alright, so with remote sensing techniques, there have been studies that have been done on impact craters on the moon and also on Mars. These two bodies are much more common to be exposed to impacts, especially the moon, for three main reasons. So the first reason is that most impact sites on Earth are in the ocean, where the craters are buried by marine sediment or which have been destroyed by plate tectonics processes. So if you remember, much of or pretty much all of oceanic crust is relatively young, as the subduction of plates happens mostly on oceanic lithosphere. So oceanic lithosphere is going to subduct underneath continental lithosphere always, and so that means that at a subduction site, you're going to have, or subduction zone, you're going to have oceanic crust being removed from what we would be able to study as. So if there had been craters that had actually impacted the oceanic crust, it's harder for us to examine them, and second of all, they are either lost completely by the process of tectonic plates or by burial from the marine sediment that continues to, be deposited. Another reason is that impact craters on land are now generally subtle features that are eroded, buried, or that have been covered with vegetation. Or maybe it's a combination of the three. So for example, in the last slide, we saw the Manicouagan crater in Quebec, and as you can see, it's both eroded, it's been infilled, and it's covered by vegetation. So all of these three things, make it harder for us to identify craters and study them. And then the third reason why they're more common to be found on the moon especially is because smaller meteoroids and comets tend to burn up and disintegrate fully in the Earth's atmosphere before they actually strike the surface, which is not the case for the moon, as the moon has no atmosphere. So the atmosphere itself, as we had said earlier, is going to cause these bodies to heat up immensely, and if they're relatively small, they're going to burn up instantaneously before they can airburst, they can explode, or they can impact the surface. So that's why we are not able to study them. Large impacts and airbursts happen pretty much everywhere in our solar system, which is awesome. In fact, a comet that happened to be intersecting the orbit of Jupiter was, studied for 21 years. Recently, as of I think it was in 93 or in 2001, I can't remember which of the two, it actually fragmented in 21 pieces. And these 21 pieces were known as a string of pearls. And later on, it entered into Jupiter's atmosphere, or all of those pieces entered into Jupiter's atmosphere, and they exploded as airbursts. So the image that you have here, here on the slide, actually shows the immense gas plume from that event. So here you see how that explosion, those airbursts happened, and this is 5 days after the explosion. This is 3 days after, this is only 1 day after, and this is right upon impact, or right upon the airburst of those pieces that were fragmented. So the plumes that occurred, as you're seeing them here on the image, were 3,000 kilometers in altitude. 3,000 kilometers, just to put an idea in your head, is about 340 times the elevation of Mount Everest. So much, much taller, or way above the surface, I should say. And then the gas plumes themselves created rings that were greater than the size of Earth. So these spots that you're seeing on the surface of Jupiter, or sort of on the surface to our eyes, were bigger than the size of Earth, which is just mesmerizing how big an explosion can be and what it can create. All right, so in this slide, we actually are going to talk about a few concepts that we should have touched based upon, I think, in chapter 1 or chapter 2, but just to bring it together in terms of what the impacts cause on Earth. So, for many hundreds of years, the idea that the Earth could be hit by large objects from outer space was really not accepted, despite the numerous eyewitnesses' accounts on various parts of the world that impacts had happened. So one of these was the lethal meteorite that landed in Israel in 14,020 years before Christ. But despite all of these witnesses, or the accounts of the eyewitnesses, there was still a lot of hesitation towards admitting that that could happen. In the 15th century, actually, Galileo had invented the telescope and suggested that the Earth and other planets orbited around the sun. That idea, however, was the one that got him jailed at the time. So it was very not accepted for many, many years, many centuries, any idea that had to do with this type of events. Or any space-related idea that we were not the center of the universe, and so on and so forth. So in 1654, Archbishop Usher of the Anglican Church of Ireland proclaimed that the Earth was created 4,004 years before Christ, which makes the Earth, if that was to be the case, approximately 6,000 years old. So this was the dogma at the time. This is what they believed. And again, he did this based on historical, biblical events mostly. And because this was the dogma at the time, there was really not much room for discussion. But with this belief, many scientists that were studying mountain ranges and large river valleys became to be at odds with that understanding, with that idea. Because if that was to be the case, then how did all of these Earth features happen to be in such a short amount of time? They realized that the mountain ranges and the river valleys, for example, would have taken many, many more years than only the 6,000 years that the Earth has been around for to be created. So, Usher proposed that Earth's features and processes were actually made by catastrophic events, so that most features happened to be catastrophic in nature. So that brought along the idea of catastrophism, okay? So, again, in his mind, this explained large biblical events as well, such as Noah's flood, but really it didn't explain much else aside from that. So he brought along the idea of catastrophism in order to make the Earth be as young as he said he was, to fit it into his idea that that's how old the Earth was.